these for walking robots, regions of attraction for walking robots, and we've been increasingly doing stochastic versions of the algorithm. I'll tell you a little bit about some of these as we go forward. So let's just think about the pendulum example now. So if I were to take the pendulum, look at the dynamics around the top, linearize the dynamics, and design an LQR controller, then that controller, and limit the gain of that controller. And that controller is going to work where the linearization was a good approximation. At some point it'll go too far and it'll fail. So the Lyapunov region of attraction analysis of this will carve out a conservative approximation. Everything inside this ellipse is guaranteed to be stable to the fixed point. It could be that the real region of attraction is a little bigger, but this is a conservative, fast approximation that proves that every initial condition in here, subject to the LQR controller, will make it to that unstable fixed point at pi 0. Okay. But if you want to do more than that, linear control at the top might not be good enough. One of the ways we would do more than that in robotics would be that if we wanted to swing up from the bottom, we might plan a trajectory with the motion planning to get it to swing up to the top. Okay? Maybe we even stabilize that trajectory with time varying feedback, and we'd like to compute something about that, somehow prove the stability of that motion too. So we can now do the same thing where we now compute a finite time invariance. So if what are the set of initial conditions around this initial condition that will stay close to this trajectory and make it all the way to that other region, and we can compute that efficiently with the same tools. Okay, and stability is not required for finite time problems, of course. The notion of optimizing volume, and this is more complex, but we've got some heuristics. We can do higher order Lyapunov functions. Some people think that when I say convex optimization, that means that I can only look for convex regions. The region is not has to be convex. We can find this is an artificial vector field created to have the true region of attraction be known and squishy, elongated, and we come up with pretty good approximations pretty quickly with the algorithm. The yellow is the approximated region of attraction. Okay, this is just another example of a known region of attraction that we estimate pretty efficiently. If you want to do robustness analysis, it fits in. The Lyapunov analysis has always been good for robustness analysis if you're willing to do common Lyapunov functions. So you just ask, I'd like that. So now the dynamics might have mass equals 1, it might have mass equals 2, as long as for every mass in the possibilities, it's always going downhill on this Lyapunov function. One Lyapunov function that's always going downhill, that's called a common Lyapunov function. That proves robust verification. And so this is just an example of the quadrator with uncertain mass doing robust verification. You can handle saturations and obstacles. In fact, you can even handle them sort of as a post-processing step. So I could take a plane flying through a polygonal forest, compute what its region of attraction or its finite time invariance around a trajectory